Let's review some things about graphs of functions. So one way to describe a function is by formula. This is very typical to write f of x equals x squared and call it a day. But another way to describe a function is by providing a graph just from the get-go. Like that's how the function is introduced. So first of all, let's just put a little reminder in of the connection between a function written in the format of notation, like f of x equals x squared, and how you get the graph. So what you do is you replace the f of x with a y, so we'd be looking at y equals x squared. Well, that's an equation in the two variables x and y, and we had previously talked about what a graph would look like for an equation in x and y. It's just every point that satisfies the equation is part of the graph, and every point that doesn't satisfy the equation is not part of the graph. So what would the graph of f of x equals 2x plus 3 look like? Again, replace the f of x with y. You're looking at y equals 2x plus 3. And just in a general sense, again, it's just all the points x, y that satisfy the equation y equals 2x plus 3. But we happen to know that if you graph this, you would get a line of slope 2 and y-intercept 3. In general, replace the f of x with a y, and you have an equation in x and y, and then you'd graph that. So again, recall that the point xy is on the graph if xy satisfies the equation, and the point xy is not on the graph if xy doesn't satisfy the equation. So if we were to graph f of x equals x squared, again, we replace the f of x with a y. So we need to graph y equals x squared. And when you're doing this for the first time, you can make a chart of x and y values, but eventually you have to not rely on this method. This works for some cases, but it's just not going to work overall. I think the part of the issue is sometimes people draw things that are only looking like straight lines, but many graphs we have will not be straight lines. And so you have to start using the method of these charts to build, aha, that's what this type of shape looks like. So here, just to pick some numbers, x is 3, 2, 1, 0, negative 1, y values would be 9, 4, 1, 0, 1, because every time the y value is squaring the x value. Now, the points 3, 9, for instance, and the point 2, 4, and, well, the point 1, 1, and so on, these are all part of a parabola. Let's click on this link to see what that looks like. So we see that parabola here, it's y equals x squared, shown in red, but we could go back to function notation, and we'll turn that on here, and that's in blue. So now it looks a little purplish because the red and the blue occupy the same space. It doesn't matter which one you turn on, which one you turn off. So one's technically the graph of an equation, one's technically the graph of a function, but it happens to be the same graph. And you have, for instance, the point 3, 9 and the point 2, 4 shown here in purple, and the point 1, 1 shown in black, and the point 0, 0 shown in red, and the point negative 1, 1 shown in blue here. So all these points, and many, many more, are all points that are on the graph of this function. Okay, so let's take this connection up here and now find, well, let's answer this question. Here's a function, f of x equals 3 to the x plus 10 times x. I'd like to find a point on the graph of this function. Just any point, meaning we need to pick either x or y, and it's going to be much more convenient to pick x. So I just picked x to be 2 because 2 is a relatively small number. And we'll find f of 2, so it's 3 to the 2 plus 10 times 2 ends up being 29. So this means that the point 2 comma 29 is a point on the graph. Let's click on the link to see a picture. Alright, so here is the function, f of x equals 3 to the x plus 10x. It looks like it's a straight line, but it's actually not. You can maybe sort of see that it's bending a little more sharply as you go up. But the point 2 comma 29, that should be a point on the graph, and it is right there. Okay. Actually, the further you zoom out, the more you can see it looks like a straight line, though it's not, and then you see this kind of bend that occurred right here. Okay, so all of these are examples of trying to get at the fact that a function is always related to its graph. And how? How does that happen? Well, each point, so the point AB is on the graph of the function f, if and only if f of a is equal to b. Okay, another thing to review is that a function, it's really defined in these three parts. So a function, first of all, has a set of inputs called the domain. A function has a set of outputs called the range. And a function is a rule which provides exactly one output for each input. So this third thing, this is a rule that provides exactly one output for each input. That's the most important part of this. Because it's so important, I want to say the same thing in different words. So restated, it would be per input, there's only one output. I want to remind you about the vertical line test. So if you have a picture or a graph passes the vertical line test if every vertical line intersects the graph at most once. So this is an important thing, is that every function's graph passes the vertical line test. So why does the graph of every function pass the vertical line test? And it goes really to the fact that a function provides exactly one output for each input. It's really quoting this part of the definition of a function. So wait a second, for each input, or per input, you only get one output. And remember, per input, like input is right here, it's being represented by an A. When you have that input, the point is you only get 1 point for that x coordinate, and you don't get 2 points in the graph which have the same x coordinate but different y coordinate. And that's why every time you draw a vertical line, you can't get 2 points of the graph, because you're not going to get 2 different points with the same x coordinate, not in the graph of a function. Okay, so the graph of a function, really due to the definition and a couple other things like the connection between a function and its graph, because of these things, the graph of a function must pass the vertical line test. Now, I want to remind you, what about like x minus 3 quantity squared plus y minus 4 quantity squared equals 5? That's a circle. That equation, if you graph, that's going to be a circle of radius root 5 centered at 3, 4. And a circle doesn't pass the vertical line test, right? You draw certain vertical lines and it'll go through the circle twice. Okay? Thus, this is not the graph of a function. It is a graph of an equation in x and y, but it's not the graph of a function, because a function's graph has to pass the vertical line test. The graph of the function f of x equals x squared is the graph of y equals x squared, which we saw, and we saw that that was a parabola, and that certainly passes the vertical line test. The graph of the function f of x equals 2x plus 3 is the graph of y equals 2x plus 3, which we had mentioned. We know that that graph happens to be a line of slope 2, and so it's a line. And this line, because of its slope being 2, everywhere you draw a vertical line, the vertical line will go through this line in exactly one place. And so the vertical line test passes again. Let's graph f of x is equal to absolute value of x. Now, if this is new, when starting, if you have not graphed this before or it's been a while, then you make a chart of x and y values. But eventually, you have to rely on something else. So you have to graph this one enough so that you're bored of making this chart of x and y values. You cannot rely on this alone. This cannot be the only trick in your bag. It's going to cause trouble later on in the course if the only way you graph a function is by making a chart of x and y values. But first time around, it makes sense to do. So x value is 3, 2, 1, 0, negative 1, negative 2, negative 3. The absolute value is always going to take a number and make it positive. So that's why the y coordinate column has 3, 2, 1, 0, 1, 2, 3. If you were to graph these very carefully, it will look like this. Let's click on the link. Okay, here's what the graph looks like. It's a V shape, right? So for instance, you have 5.4 comma 5.4, but you also have over here 5.4, I don't know if I can write it, yeah, negative 5.4 comma 5.4, because the y coordinate is the absolute value of the x coordinate, right? Y is absolute value of x. So you get this V shape. It's like a line of slope 1 and a line of slope negative 1 met right here at this corner, and there's this 90-degree angle created right here. So this shape is really important to know and keep track of. I'd like to graph, oh, there's a typo here. I'll fix this when uploading. But I'd like to graph f of x is equal to root x. So apologies about the 25 here. I don't know how that got there. So again, when starting, make a chart of x and y values. But eventually you have to rely on something else. So because there should be an x here again, maybe I'll just fix this on the screen real quick here. Can I do that? Let's go ahead and give this a try. Okay, there. Sort of did it, right? So f of x equals root x. Okay, so when you're starting, make a chart of x and y values, but you have to rely on something else eventually, not just that. So for the values of x, I didn't just pick 1, 2, 3, 4, 5, 6, 7. Right? The thing is, since you have to end up rooting x, it makes much more sense to pick perfect squares for x. So 0, 1, 4, 9, 16, 25, 36, and so on. These first couple numbers people kind of get a little tripped up on, but I want to remind you what a radical is. So why is there a 0 here in the y column? Well, because root 0 is 0. And it's because this 0 squared equals that 0. So root 1 is equal to 1 because this one here squared is this one. Root 4 is 2 because this 2 squared is this 4. Root 9 is 3 because this 3 squared is this 9. So I'm using the same language here. I just run into this weird coincidence of the same number appearing, but it's not because it's copied over. We're just processing what a root does. Let's see a picture of that. Okay, so sometimes when people graph this on paper by hand, the points themselves somehow lend people to thinking that you're going to have just a straight line accidentally or something like that. But you don't. If you graph 0, 0, and 1, 1, and 4, 2, and 9, 3, and 16, 4, and so on carefully, notice that like you travel 1 unit up, but you would travel not always the same distance horizontally. Yeah? So it's 1 unit up, 1 unit to the right, but then it's 1 unit up and then 3 units to the right, and then 1 unit up and like, 5 units to the right or something like that, right? So each time you go up 1 unit, you have to travel more to the right. So it's not a straight line. It is not a straight line. It is a curve of some kind. Yeah, so this is y is equal to root x. What it really is, let me maybe just kind of unhighlight these specific points on this shape. If I zoom out, what it really, truly, honestly is, it's actually a sideways parabola, and it's just half of it. Okay, so we've looked at several major important functions and their graphs, but there's an important expectation that we should talk through right now, and it is this. There are some standard functions for which you should know the graph. Now, I don't mean right now, right this minute, but I mean you have to get familiar with certain graphs, and you have to know what they are. I just want to make that expectation very clear. So how? By making charts, XY charts in the beginning, but then not doing them again for the same function too many times. So you should do it. You should practice. That's the only way. To get good at this is you have to make these XY charts, but make them often enough to be bored of doing so for these functions. So once you're presented a certain function, you make that XY chart and go, okay, that's what it looks like. And then you maybe get the same function again later, and maybe don't even realize that when you build the XY chart, you're like looking at the points and you're drawing them, and you're like, wait a second, I've seen this before. And so once you do that enough with the same function over and over, you have to stop making the XY chart. At least for that function, you got to say to yourself, wait, I've already done this one, right? So here are some functions that are, to me, considered very standard, and you need to know what these look like. So practice by building the XY charts yourself for these. Verify using Desmos. So y equals x squared. That's this. This parabola, you might have memorized that. That's what it looks like. But build the XY chart once, twice, 3 times, 4 times. But then, you don't really want to build this XY chart for y equals x squared 20 different times or 30 times, right? So same deal. Y equals absolute value of x. We saw that V shape just a moment ago. Y equals root x. We saw this sideways half parabola. These are extremely common and very important. And with what we're going to do with these in the class, you just won't have time to continue to build the XY chart every time separately. And we're going to do something additional with these where we're going to have to zoom past just making XY charts. Also, what if you had the function's graph was a line? So any line, such as y equals 3x plus 5. Or how about y equals 2x minus 1? Or y equals 1/4 x plus 7. So all of those. And then here are some that are a little more rare, but I do want you to give this a try and draw XY charts for y equals 1/x. Or how about y equals x to the third? Or how about y equals x to the fourth? Give those a try. Again, create a chart of x and y values at first, but then become so familiar with the shapes that appear the most often, so that you don't have to draw XY charts. Okay, what practicing this does is it helps actually reinforce what that connection between a function and its graph is, namely that the point a comma b is on the graph of f if and only if f of a equals b. Why does it reinforce this? Well, because as you pick a random value of x and you compute what y is, and you put that info in a chart, you also have to graph that point. And so it's really creating this connection that, you're computing like, f of, maybe you plug in 3, and you get 9, right? So 3 squared is 9. So then you have that point 3 comma 9, and it's helping reinforce what this connection is, and that's good, but don't rely on the charts alone because we have to do other things, and so we're going to have to run with things in a moment. So use the charts, but my point is, as you do it, don't just use the chart to create the graph. Use the chart to create the graph and then stare at the graph and go, I want to be familiar with certain graphs because certain functions will appear so often, such as y is equal to x squared. Okay, so again, to say this a little differently, to clear up expectations, let me talk in first person. Let me talk about me. Now, since I've practiced, I don't make an xy chart anymore for f of x equals root x because that's one of the familiar ones. It's like one of the usual ones in the list, okay? However, I do make an xy chart for a really wacky looking function like f of x equals x minus 7 quantity squared minus x cubed plus 8 over x. That's got so many things going on in it. If I need to graph this by hand, I would be making an xy chart.